Okay, so my presentation today is going to about my project, a novel trap-assisted tunneling-based ferroelectric tunnel junction for performance improvement, a theoretical investigation. And I'm a student, Gong Sixi, and my advisor is Professor Alex Ho. Journal flow is going to be first introduction, then simulation method, and then results in discussion, and finally conclusion. Okay, so we need to first know what is FTJ, which is ferroelectric tunnel junction. FTJ is a non-volatile memory which has the prefix assumption and it's seamless compatible. And despite these benefits, it actually encounters significant limitations in memory computing, which because it has the current density and low R ratio, and the R ratio is defined by the on current over the off current. So we expect the performance to be higher if the off ratio is higher. And in this work, we propose a novel kind of FTJ, which is TAT-based FTJ. And we believe that if by appropriately modulate the trapezoids in the FTJ, we can make the performance of FTJ to be achieve higher current density and also a higher off ratio compared to the fundamental FTJ. And in the past research, there's actually already have experimental results about the 3 nanometer HZO FTJ have its current density and R ratio both increased after inserted by an additional 1.5 nanometer aluminum oxide. And this result can be simply explained by the direct or FN tunneling because the thickness of FTJ becomes larger. And we normally expect that the current density should be lower. Well, however, it didn't. So we believe that there's some traps in the FTJ that cause this to happen. Okay, and in our work, we developed a comprehensive model that integrates direct FN tunneling and trap-assisted tunneling all together, and through this comprehensive model, we simulate the experiment in the figure C, and it's clearly seen that they shows a group agreement. Okay, and the band structure is shown in the figure E here. Okay, so this is our simulation method, and I'm not going to go through the details because it's relatively complicated. This is the results in discussion, and we first investigate the trap condition optimization. And in the figure A and C here, you can see that there exists an optimal trap condition that can makes the current density and the on ratio to be very large. And this is a pretty significant result. And you can see here in the figure E that the TD-based FTJ exhibits a significant advanced performance over the fundamental FTJ. But we need to, it's worth emphasize that in the figure A and C here, you can see if the trap condition is slightly deviates from its optimal value, that either the current density would decrease very fast or the R ratio would degrade very fast. So, uh, so previous research might have systematically overlooking the potential of our novel TAT-based FTJ due to this reason. Okay, so based on the trap condition optimization, we further do the device structure optimization. And in the figure A and B, we do the thickness scaling for the TAT-based FTJ and fundamental FTJ, and you can see that the on-current density can be increased while the on ratio would degrade. So in the figure C, we do the on ratio optimization by modulating the thickness ratio between TL and FE. And because the trap condition optimization point differs between different device structures, so we do the trap condition optimization again in the figure DE and eventually in the figure F. You can see that the performance of TAT-based FTJ reaches J on higher than the 10 to the power 5 A over C squared, and the R ratio, which is J on over J off, is approximately 170. And this is a really, really remarkable performance achievement in the ferroelectric tunnel junction. So here's a conclusion that even slight deviations from the optimal trip conditions can easily result in leakage or extremely low TD current, that leading to the systematic overlooking of the potential of TAT-based FTJ. And in our work, we provide the guidelines for optimizing trap conditions and device structure. And eventually, we demonstrate that the TAT-based FTJ exhibits significantly improved performance compared to the fundamental FTJ, and effectively addressing the critical bottleneck that FTJ has encountered.